This is Jim Hendershot again. We're going to present lecture number 16. This is a overview or an induction to polyphase induction motors and historically why they're designed the way they are and how those designs relate to the designs required for inverter drives. My own opinion about this machine is that it's almost magical. It's technically the most elegant machine ever invented by man. It's quite an amazing thing that we could take electromagnetic energy, put it in wires in a stationary part of a machine, and have it cause the shaft to rotate without any wires or anything connected to the rotor. It's called asynchronous, which the definition of that means without synchronism. It's a type of electric machine where, as I said, AC power is directly applied to the stator windings with no electrical connections to the rotor. The power enters the rotor by means of electromagnetic induction rather than direct connection to an external supply through slip rings. Although, having said that, it is possible to take the rotor in the machine that you see up there in either one of those pictures, and instead of die casting aluminum conductors or copper conductors down the slots, you can wind a three-phase winding there, put slip rings on it, and control it with an external inverter. Even though the rotor speed's not synchronized to the rotating stator speed, which is called slip, the induction machine is constantly trying to synchronize itself. So I think of it as asynchronous means without synchronism, but I like to take a little definition of liberty with that term and call it a synchronous wannabe. An induction machine or asynchronous machine is a synchronous wannabe. So how do you control the speed? Basically, you control the speed of this kind of a machine by adjusting the AC applied frequency, and the torque output is controlled by basically how much it slips, how much the induced rotor poles slip as the rotor is rotating. Because the rotor poles are in synchronous with the stator poles, but since they're not glued there, since they're induced there, they slip, and so the rotor rotates slower than the poles are rotating that are induced on the rotor. That's where the slip comes from. Now, so the greater the slip, the higher the torque, but that's not a good way to control torque. You can also control the torque by adjusting the voltage, but that's not a good way to control it either. And we could study the pros and cons of why I say those methods aren't good. We can see that from the classic torque speed curve of an induction machine when it's driven by constant voltage and frequency, which we'll look at. And that leads me to the most important point about this whole lecture is the fact that the existing induction motors we find out there on distributor shelves, and the one we're most accustomed to, their original design criteria when they were first conceived was based on the assumption that they're always going to be powered with a constant AC voltage at some frequency. Now we have voltage standards and frequency standards in about every country. In the United States, the frequency standard is 50 hertz. In Europe and much of the rest of the world, it's 50 hertz. So the characteristics of how the machine performed at fixed voltage and frequency caused the designers to optimize the rotor configuration and the stator to some extent, but mostly the rotor configuration, so that it would give the desired performance at a fixed voltage and frequency. Now the motor torques are produced in the air gap from the flux linkage between the two magnetic circuits, one in the rotor and one in the stator, just like the brushless, just like most all machines are. Most all non-salient pole machines are produce their torque that way. And the voltage and current is supplied externally from power source only to the stator. There's none directly applied to the rotor, as we said many times before. The rotor currents induced in the rotor conductors, whether they're caged or wound. Well, if they're wound and connected to an external supply, they're directly applied through slip rings. But if the windings are in the form of a cage that's short circuited with no external connections, then the rotor currents are induced in there. The current then that the stator draws from the supply consists of two current vectors. One of the current vectors, or part of the current that the stator is flowing in the stator, is used to magnetize the magnetic circuit. The second current vector is the current that's used to produce torque, and that current is what flows in the rotor bars. What the current that flows in the stator is the vector sum of the magnetizing current and the torque producing current. And the magnetizing flux created by the magnetizing current induces a voltage which produces a current into the rotor conductors, and that's the current that controls the torque. So what an inverter does is take those two current vectors apart and control them separately. So what we want to do is discuss what characteristics of the rotor design have to be optimized, and what do we need to do to them that's different with respect to a motor that's going to be controlled with a current of two vectors and not allow it to be done automatically by the fixed frequency, fixed voltage, slip, and changing loads. So in summary, the principal difference between a grid and inverter-powered AC machines is a rotor bar configuration, how the rotor is made. The materials used for the steel core is about the same. You use steel for the rotor core and the stator core, same electrical steels we use in all machines. You typically, small induction motors, or I don't know what the size is today, maybe under 500 horsepower. 500 horsepower and under are all aluminum die cast, and the ones that are larger than that have fabricated rotors because the die casting dies get too big, I guess. I don't know how big they die cast machines now. But if you can't die cast them, you have to fabricate them by hand. You have to have separate bars and end rings, and then you have to weld them or fuse them together somehow. And if you're going to do that, you can use copper rotors as well. And copper rotors are used in a wide number of machines. We'll just be discussing that. As we said, the rotor windings consist of a single shorted turns with a lot of parallel paths for those turns for the current to flow, and those parallel paths go through what we call the rotor slots, through the rotor bars. They're shorted from end to end with end rings. But the current doesn't flow in the same direction from one end to the other in all the rotor bars. Some of the bars will go from left to right, let's say, and that forms a north pole, and then adjacent on either side of that group of bars, you'll have the current flowing in the opposite direction, and that creates the south pole. And then as it rotates, the bars in between those adjacent poles has a current direction reversal taking place. So it's very complicated what goes on in there. The other issue involved with these machines, as we'll see when we have a look at the torque speed curve, is the starting torque. One of the characteristics of an induction machine is that if you operate or drive or power induction motor on a fixed voltage and frequency, if you have a low resistance in the rotor cage, you have low starting torque. If you're all of a sudden trying to start it with a fixed frequency without ramping the frequency up. If you have started with instant voltage and instant full frequency, then your starting torque's very low if you have a high resistance rotor. What you want is a low resistance rotor. You want the resistance to be low in the rotor, and that gives you a high starting torque. But the problem with that is if you have a low resistance rotor, when you're up at rated speed, your heating and your losses in the rotor are so high it gets very hot and it affects your continuous efficiency. So what you really want is a rotor that can be designed that has high resistance during starting and lower resistance during running. So that's the fact, or the dichotomy, or the characteristic of a machine, induction machines that dictated how the rotors were designed for the last 100 years. But that problem goes away when you drive it with inverters, and we'll study that more in detail and say that over and over again several times. So standard NEMA and IEC induction motors, they're really not optimized for flux vector control or control by two current vectors. They're optimized to run, to give good starting torques and good running efficiencies with constant grid frequency and voltage. And of course, the number of poles is another issue. If you increase the number of poles over 4 on up to a 1300 Newton meter motor, there's a reduction in the power factor and the efficiency by increasing the poles because of the reactances go up. And the other difficulty with induction machines is the heating that's caused in the rotor. There's a rotor in an IM has conductors that carry current, so there's I squared R losses. So you have to get rid of that heat, and that's what limits the steady state continuous performance of an induction machine, is the heating in the rotor. Here's a picture of a very large induction machine. Shows all the components, and I like to show this picture because we see here the ventilation vents, the cooling vents. We see here also a copper rotor, not an aluminum. You can tell by the color it's copper. And you see that the bars that go down the core pass through these cooling vents. And the bars extend past the core before they're attached to the end ring. The end ring is not right up against the core like it is in smaller die-cast aluminum machine. There's two very good reasons for that. One, the idea this copper will suck air as it spins. These bars become centrifugal fan blades, and so it circulates air, and that air blows on the idea of the stator winding. So not only does it cool the rotor, but it cools the stator as well. So you have built-in fans for free. But that's not the main reason this is done this way. These bars are extended because this rotor is so large. The thermal expansion rate of steel versus copper is so much different that copper expands more than aluminum per degree C, or more than steel per degree C. So what happens is, if this were right up against it, there would be tremendous stresses on the bar right at the intersection because the steel isn't expanding as fast as the bar. So you continually stress these bars to the point they'd work harden and eventually break. So, and we're going to talk more about that. But there's also a fan in here that helps focus sucks the air through these louvers that forces it to go inside this end ring and be thrown out by these blade effects of the extended bars to cool not only the rotor but the stator as well. This is courtesy of Siemens. Here's a cross-section of a very high-performance induction machine that's used in things like machine tool spindles. You see that you have your rotor core and your stator core. Here's your die-cast rotor end rings, and the conductors go all the way down through here. And this one happens to have a liquid cooling jacket around the outside. It's sealed air, and you bring liquid, big coolant in here, and it goes around these spiral grooves in the OD and exits the other end. So this coolant can be cooled in a radiator-type heat exchanger, or it can be cooled with a refrigeration unit, which many machine tool spindles have refrigeration units. And of course, you've got precision bearings, large shaft diameter, all those sort of things. So some machines even have hollow rotors, and they have heat pipes in them to take heat out of the rotor. I don't have any pictures of those, but this is what I was talking about before, about the torque speed curve with fixed voltage and frequency. And here we see the motoring region and the generating region. And so when you're motoring, the motor is trying to run at synchronous speed, 100% synchronous speed, but whatever load's applied on is going to slow it down. So it's going to slow down to this point until it hits the breakdown torque, and then it's going to stall. Now when you start an induction motor under load, this is the starting torque. If you have a high resistance rotor, it'll put the starting torque up here, but then your slip will be greater. It'll slip like that, and so you won't run at very high efficiency up around operating speed. Now in generating mode, what you do is you crank the motor faster than the synchronous speed, and so now you have a positive slip instead of negative slip. And so you're really exciting the motor, but you're getting more power out than you're putting in. So you have a positive slip instead of negative slip, but only up to a certain point, and then it'll stall as well. It may not stall the prime mover, but it'll apply. The torque will go up quite high, and then the torque goes way down, of course, as you go faster and faster. So you would never speed it up past, as a generator, you'd never speed it up past maybe 105, 110% of synchronous speed. You'd never operate a generator down this range. It's crazy. Here's a picture of some more details of these machines. This is a nice picture showing the rotor and the stator and the die-cast rotor, where the die-cast end rings are cast right up against the core, and these are cast fan blades here. So when they spin, there's some holes in the end of some of these things. Sometimes here's your holes in the end. No, they're in the end of a cover. This is a totally enclosed motor. This has a fan that sticks on the back of the shaft, and it sucks air in here and blows it out over the OD over these fins. But these fan blades here, all they do is circulate the air inside of the end turns here to cause the air in there to not cavitate against a smooth surface, but to be thrown out by these centrifugal blades against the end turns, and that in turn throws them out here to the surface of this aluminum end cap. Sometimes you even have fins on those, and so that circulation of the air gets cooled by its contact with the end ring. It's not real effective, but it helps. It works. And here's a machine where the core is put inside. You see all the coils and the end taping and lacing in the end turns. There's the lamination core without the coils in it. Here you see a cutaway provided by a machine tool spindle company in Switzerland called E+A, E+A. And this shows the copper bars, the copper end rings. This is a small one, so the bars are, they silver solder these bars to that ring. They use round bars, and they silver solder that. And here's your windings and end turns for the stator. This is a picture of this happens to be an aluminum rotor there that's been die cast. That's the same type that's in here. And there's your blades. But here's two examples of copper barred rotor. This one here with the round bars is the type that's in this E+A motor. And but this one has some teardrap slots, and this one was die cast. That's a new technology to develop to be able to die cast copper rotors. That's been developed first in France and probably China and Japan. I don't know, but I know a French company is noted for this. But there's also a company in Ohio called Ramco, R-A-M-C-O, that's not using the French technology. They're using their own, but they die cast copper rotors as well. Tooling's expensive, but they can do it. Now let's talk about the laminations that have been designed for induction motor rotors used with inverter power with constant voltage and frequency. They've classified these into four classes. NEMA type A, B, C, and D. And stator designs for the last 100 years have been one of these four types, and each one, as you'll notice there, has different shaped slots and or rotor bars. Most of these are die cast, but not all of them. The rotor bar shape has been optimized for the starting torque requirements, and only NEMA A and B is suitable for inverter operation. These other two aren't suitable for inverter operation, so you wouldn't want to use them. So, and even the type A and B for a certain frame size might need to be modified slightly to get the best performance out of a machine that size using the inverter. So let's look at what those differences are. Oh, this slide doesn't really belong here. We've looked at this before, but we're gonna. I guess somewhere else I'm going to talk about the differences in these slot designs. But so let's follow the slides here. This is a power flow from electrical power to mechanical power from left to right. And we saw something like this in one of the other lectures about the state. You have stator core losses, rotor core losses, windage and friction, and those are core losses. But you also have stator resistive losses and the rotor resistive losses. And I don't know why I stuck that right in there, but here's a picture of some more cage rotors, and I think it's important to go over these. Here's an aluminum one with bars extended past the length of the core, and there's vent passageways through the core. Here's another very strange looking rotor construction. Here's your flat rectangular bars that go down the slot, and they're somehow attached to a ring of copper here to make a squirrel cage. This is another example of a fabricated rotor with cooling vent passages through it, and the bars are spaced out past the end ring, and this has a cooling fan added to the end of it. Now this is very interesting. I referred to this before. Here, this is one bad die casting job. That would be scrapped. You see, this is the alignment of the laminations when they're skewed in the tooling is so bad that you've got places here where you can't even get the current to flow through here because it's offset, misaligned so bad that you completely blocked off the aluminum there. There might be just a thin, paper thin connection between this part of the bar and that part of the bar there, which is going to be a very high resistance point. So that's very critical. You want to avoid that. This is a cutaway of an induction machine that has a wound rotor and 3 slip rings and brush rigging on it, so that this is the type of machine that's used in a wind turbine. And these are built in the megawatt sizes, very, very large machines. They originally were used for overhead cranes to get real high starting torque. The fact that you had external connection to the rotor, you could add series resistance in series through the brushes and slip rings to give a real high resistance to the circuit, so that you would have high starting torques to lift loads, but only for a few seconds. And then you would externally short those out, so then it would run at full speed, just like a regular induction motor with no external series resistance. So the same mechanical configuration of the machine, the number of turns are different of course, is used for wind turbines, so that this winding is excited by a 3-phase AC inverter, taking power off the grid, but only about 1/3 of the rated power of the AC generator is taken off the grid. So you use 1/3 of the power, but you generate the other 2/3. So you generate a lot more than you use. So that's one reason why they're so popular. Plus, they're easy to synchronize to 60 hertz. So this is an example of there's a picture of a little rotor, induction rotor with a wound field and 3 slip rings on it. And here's an example of what the torque speed curves looks like with what happens to the slip, what happens to starting torque. Here's the lowest, this green curve has the lowest starting torque, but it has the lowest slip, so it runs at the highest efficiency if it's running up here. And that's the breakdown torque. Now the red one has a higher resistance rotor, so it's got high starting torque, but the slope is also more, so the slip is higher if this is your torque value you're after, that's the slip for this rotor, that's the slip for that rotor, and a whole lot of slip to get that much torque out of a rotor that has high resistance is putting out a very high starting torque. So this is what I was talking about before. There's your wound rotor, and your brushes and your external variable resistors are used to adjust the starting torque. So that what you could do in this case, you use the series resistors to get the starting torque, but then you short those out so that when you're up to speed, it operates on this slope line. This is the equivalent circuit of one phase of the induction motor. This is used a lot to predict the performance of motors. It's been used for 100 years or so. And what it boils down to is it's a circuit of one phase of the primary of a rotating transformer, and the circuit of the secondary of that phase. And this is the rotor cage has the same circuit as the secondary of a common transformer, and the rotor cage is treated as one circuit for the rotor because it's equivalent to a single turn secondary. It doesn't have 3 phases, it's only got 1 phase, even though the 3 phases of the stator field will induce the right number of poles in the windings of the rotor. This is the complete equivalent circuit, and all the motor parameters. All these motor parameters can be measured, and the performance of the motor can be calculated. You can take an existing motor and measure the equivalent circuit parameters, the voltage, the the resistance, the inductance, the reactance, and from that you can calculate the current, you can calculate the torque versus speed, power factor, efficiency, and magnetizing current. You can calculate these things from the equivalent circuit parameters that you could measure off an existing machine. We're going to go over that later and go over how you measure those. And if you have some software tools, or you have a list of all the equations to calculate these things, you can estimate and calculate all of those equivalent circuit parameters too, as well. And so the best way to calculate the performance of induction machines is calculating the equivalent circuit. This is a popular wind turbine that I mentioned before. You use a 3-phase inverter at about 1/3 of the total energy used for the rotor, and you get a lot more energy out at the stator. Now, I don't know why that was inserted there. I'm not sure it belonged there. But when induction motors were powered off the grid, the performance curves were shown not as torque speed curves, but speed torque curves. The speed was on the vertical axis and the torque was on the horizontal axis, because it was true that you did start some motors under load, but because of the limited starting torque, that was avoided. Even when you use induction motors for compressors, they would have check valves or relief valves in the compressor that during starting the compression would be released so that the induction motor could start the compressor at no load. Then once it got up to speed, then the valve would be closed so that compression would take place and you'd start compressing. So many motors aren't loaded down till they're already up to full speed. But if you but still this the motor's going to go through this same torque speed profile from start, whether it's loaded down to produce that much torque or not doesn't really matter. Now this is a load characteristic of something like a fan. A compressor would be different, but this is like a fan blade. So the starting torque of a fan blade is very low. You got a little friction to overcome, but it's mostly all inertia, but it really starts under no load. So it's no problem to use an induction motor to start a fan load like that. And so the torque builds up, and of course the torque requirement of the fan builds up, but the fan won't go any faster than the speed at which the intersection of the two loads cross each other. And the induction motor won't go any faster either. It won't go any faster than this RPM either, because the load is holding it there. And that difference between that speed and the no load speed, the synchronous speed, is the slip speed. And this is a breakdown torque. Now, if somehow I were to take this fan without cutting my fingers off and using a piece of wood or something to drag the fan down, slow it down, the motor would slow down, the torque would increase, and still it hit the breakdown torque, and then it would immediately stall. See, the torque is increasing, but now when it goes through breakdown, it's going negative again. So the only way I can get this to accelerate again is to reduce the load below that value, or it'll stall. And most motors, when they do stall through a load, a better way of looking at this condition is in a table saw. Many of you have used a table saw, and you're powered by this kind of a motor running on fixed voltages and frequencies. So you are sending a board, a piece of plywood, through the saw, and you bind up the saw so the saw stalls immediately. It won't start again until you move the blade to get rid of that friction, and that's what happened. The torque was at this level, that's what caused it to stall. But you've got to reduce the torque to, instead of that level, you've got to reduce the torque to this level before it'll start again. I'm sure you've all experienced that. And that's because of the fixed frequency and voltage and the inability for it to control the magnetizing current. But all that can be fixed with an inverter drive and controlling the current and the torque vector. This is a set of torque speed curves that really should have been close to this picture here. A, B, C, and D. Think of those laminations. Those laminations go with these different torque speed. Now I've changed this now and put this in terms of torque speed instead of speed torque. But those are your A, B, C, D curves. You see D, the one weird one there, that has the highest starting torque, but very high slip. Okay? Now, let's see, this one, C, has a stepped bar. It's got two sections of the bar. It's got a small bar close to the OD of the slot and a deep bar below the slot. So during starting, the current flows in the outer part of the bar, giving you this high starting torque. But once you get up to speed, the current flows in both sections of the bar, so the slope is steep, the slip is lower, so it runs at more efficiency. But you wouldn't want to use that rotor for an inverter. A properly designed 4-pole induction motor with a type A bar or a NEMA B type bar shape, teardrop shape, close to the OD of the rotor, and lots of bars. Those are the tricks. Lots of bars close to the OD and teardrop shape. Can be parallel-sided bar, rectangular bars, but teardrop or rectangular bars. So if you run, you take that motor and run it at, use an inverter and run it at fixed voltage and frequency, and do a whole family of curves, you define an envelope of a torque speed curve of a brushless motor or a synchronous motor, which is what you want. But by grid power, you could, with constant grid power, you could never, and frequency, you could never get the motor to perform into this envelope. So once I put an inverter on it, I can define a torque speed envelope that motor will run anywhere inside of this curve. Now you don't need that many curves to define that. You can do 3 or 4 curves to define that, and we're going to go over that later. But that concludes this lecture. Thank you.